Now we need to understand some behavior of the network and of the receiver process, because there are some typical overload or overflow that could happen typically in some queues or buffers. Remember, there is a buffer at the receiver side of the communication, and there is queues in the network, in the transmission network. Then, if the overload or overflow is produced here in the receiver buffer, we call this the flow control that the TCP need to perform in order to avoid the flow or overload of this buffer. And there is another phenomena, another problem to solve, that is the overload or overflow of the network. There are several queues in the network, and we need to avoid the overflow or overload of those queues. And in this case, when that overload or overflow is produced, we talk about the congestion. Then the TCP need to control the congestion. That is, implement some kind of congestion control. Remember that in every cases, the TCP will adjust the rate of the transmission, modifying the window size. Then the first mechanism that we will see is the flow control. Remember that in the receiver side, there is an application process that need to read data from a buffer, a receiver buffer. And if the information, the data that arrives to the receiver and is stored in the buffer is higher, that is arrives with a higher speed than the speed at which the application process read this queue, this buffer, then we could have some kind of overflow or overload of this buffer. Then we need to ask to the application, to the TCP in the other in the transmission side of the communication, in order to slow the transmission, to adjust the transmission rate in order to avoid the overload or overflow of this buffer. This is what we call the flow control. Then the flow control, in fact, remember the problem is the receiver buffer can overflow or overload. The solution: the receiver sends the window size. That window is called advertised window. The advertised window, indicating the number of bytes that the transmitter can send from the starting from the acknowledged number. That is, the receiver had enough space in the receiver buffer to receive W bytes starting from this acknowledged number. That's why then the transmitter could send starting at this sequence number could send a total amount of W bytes without receiving an additional window, because remember that the ARQ, the automatic repeat on query, use the concept of a sliding window. That is, starting from this number, this sequence number, the transmitter could transmit, remember, W bytes, and that W size, that window size is called advertised window. In that way, then the transmitter will avoid the overload or overflow of the receiver buffer in the receiver side of the communication. A particular case is when the advertised window is 0, and that means that the receiver buffer is full and the transmitter cannot continue transmitting, and the transmitter in that case need to stop the transmission and wait for a new acknowledge with a window different from 0. In that way, then the TCP implement a mechanism of flow control. Then this is another example. For instance, this is the receiver is empty. The transmitter send a packet of 2 kbytes. This segment arrives, is stored in the buffer, and an acknowledgement is sent. But for instance, in this case, if for instance the applications don't read this data, then the available space in the receiver's buffer is only another 2 kbytes. Then pay attention that then the acknowledged number is 2K. That is saying that the receiver already received correctly the first 2K, and the capacity available is of 2 additional kbytes. And then the application send another segment with 2K bytes, starting at the sequence number 2K. Remember, with the notation of 2K bytes, where 1K is in fact equal to 2 to 10 in 2 powers. And then the receiver side receive those 2K bytes and store them in the correct position in the buffer. But if the application don't read this information, we realize that the receiver buffer is full. Then that's why, for instance, the receiver send segment indicating to the transmitter that the acknowledged number is 4K. That is confirming, is sending an acknowledgement of the previous 4K bytes already received, but with the window size, an advertised window of 0. That is, in this way, the transmitter need to stop the transmission. The transmitter couldn't continue to send additional data. Once the application process in this side reads the data in the buffer, for instance, the application could read, for instance, the first 2K, that is the first 2K here. Then the receiver sent to the transmitter an acknowledge indicating that the the next octet that the receiver is expecting to receive is 4K, and the window size, the advertised window size, is 2K. Then, for instance, in responding to this segment, the transmitter send then an additional data, for instance, 1K byte, starting at the sequence number 4K. And then in that way, for instance, remember that that kind of buffer is in fact a circular buffer. That is, the new data is stored in the for instance, when the buffer is full, the new data is stored in the space that is free once the application reads that information, the oldest information. And in that way, the process of the flow control is performed by the TCP protocol. But there is then another problem of overload or overflow that happens within the network, not in the end system, but within the network. And that kind of problem, congestion problem, could be created, could be faced by the TCP protocol in order to avoid the congestion of the network. That is, if packets are lost at certain window size, this can be detected if the sender doesn't receive a confirmation with a certain timeout. It must be assumed that the packet was discarded by a router in the network due to too high network load. That is, the cause is a congestion and not an error. That is typically, for instance, an impulsive error in one of the links. This is, so to speak, a traffic jam on the network. A traffic jam, typically. There is typically, for instance, a queue that is overload or overflow, and one packet have been dropped because there is a congestion. In order to resolve the congestion, all transmitters involved must reduce their network load. But in this case, what we will see is that the congestion control is based in a concept of explicit congestion detection, not as in the case of flow control, where the flow control use an implicit an explicit flow control use an explicit mechanism to detect the overload. The explicit is the window size, that is the advertised window. In the case of congestion, we will see that, in fact, the detection, the congestion detection, is performed implicitly because the detection it happens when a packet, for instance, is discarded and the end system don't receive the acknowledge. For instance, the transmitter side of the TCP connection doesn't receive the acknowledgement of one segment. Then assume that the cause was the high network, the too high network load, that is congestion. Then there are typically 4 algorithms defined in this RFC: slow start, congestion avoidance, fast retransmit, and fast recovery, which are used together in pairs. we will see one by one those mechanisms. Slow start and congestion avoidance was Van Jacobson that proposed those algorithms. At the beginning of data transfer, the slow start algorithm is used to determine the congestion window in order to prevent possible overload management. That is, instead of starting at a high rate, the transmission start with the slow rate and increase the rate in each time the segments arrive without errors to the destination end system. One wants to avoid the traffic jams, and since the current utilization of the network is not known, initially small amount of data are started. We start with a slow rate of transmission. The algorithm starts with a small window of only one MSS, that is one maximum segment size. Remember this, in which data packets are transmitted from the sender to the receiver. The receiver now sends a confirmation, that is an acknowledgement, back to the sender. For each ACK received, the size of the congestion window is increased by one MSS. Since an acknowledgement is sent for each packet sent upon successful transfer, this leads to a doubling of the congestion window within a round trip time. That is, we will see that each round trip time, we will see that the congestion window doubles. We will see that detail in the behavior of the TCP protocol. For example, if the window allows two packets to be sent, the sender also receives two ACKs and therefore increase the window by two, to 4. This phase of exponential growth, also called the slow start phase, continues until the so-called slow start threshold is reached. Then we will see that the TCP uses a threshold called SS threshold or slow start threshold in order to change the behavior. After that, once the window size is reached the SS threshold, that is the slow start threshold, the congestion window is only increased by one MSS if all packets from the window have been successfully transferred. So it only grows by one MSS per round trip time, that is only linearly. So we see then that the increase of the congestion window is produced only linearly and not exponentially as in the slow start. This phase is called the congestion avoidance phase. The growth stops when the window size specified by the receiver has been reached. If there is a timeout, the congestion window is reset to 1 MSS and the slow start threshold is lowered to half of the old congestion window. We will see that particular detail. The phase of exponential growth is thus shortened so that the window grows only slowly with frequent packet losses. And this is in fact the evolution of the window size in the x-axis. We have the time where the time use the round time units, 1, 2 RTTs, 3 RTTs, 4 RTTs. Then pay attention. This is the units of the y-axis is the window. Then, for instance, remember that the window is directly related with the throughput. Then, when we increase the window, we are increasing the throughput. Remember that. Then this is the congestion window, not the advertised window. Is the congestion window, and is measured typically in a number of MSS, maximum segment size, starting at 1 MSS. After the first round trip time, the window doubles. That is 2. After another round trip time is 4. After another time round trip time is 8. After another round trip time is 16, and so on. Then we could realize that at the slow start phase, the window, the congestion window, then the throughput of the transmission is increased exponentially until the slow start. Remember, this is the slow start phase, until the window reach the slow start threshold. This slow start threshold. After that, then the window, the congestion window, will increase only 1 MSS each round trip time. Then the increase is happening linearly and not exponentially like in this phase. Remember, this phase is called congestion avoidance phase. This congestion window is increased until, for instance, a segment loss is detected. If a packet or segment loss is detected, for instance, because the transmitter doesn't receive any acknowledgement, then what happens is that the congestion window is reduced to 1. Remember, to 1 MSS, and the threshold, this slow start threshold, is set up to the half of this congestion window when the congestion was detected. Then, for instance, in this case, is the SS threshold is set up to 20K. In fact, 20. The half of this amount. I don't know if it's K or is the number of MSS. 20 MSS, 32 MSS. This is, for instance, 40 MSS. Then the SS threshold is set up to the half of 40, then to 20 MSS, for instance. Then we will see then some particular details of this behavior. Then we need to review some concepts. The problem is the congestion. That is, queues in the packet switching networks can grow, introducing delay. And when the network impairment is the delay, we talk about soft congestion, and can even overflow or overload the queues, dropping packets. Then in that case, we talk about severe congestion. When the congestion is severe, some packets are dropped. Solution: the congestion control. Then we could review this algorithm. The transmitter calculates a congestion window based on the implicit detection of the state of network congestion. When the transmitter detects the loss of a segment, it assumes that it was discarded due to severe congestion, then drastically reduce the throughput by reducing the congestion window. As it receives acknowledge, it increments the congestion window again. The transmitter implements the automatic repeat on query sliding window by choosing the lowest window between the advertised window. Remember, this is the window advertised by the receiver, and this is an explicit mechanism of advertisement, and the congestion window, that is an implicit mechanism of congestion detection. And remember, at any time, the transmitter choose the lowest window between the advertised window and the congestion window. Only simply in order to remember the different proposals of congestion control algorithm. There is a proposal called TAOE from Jacobson that includes the mechanism of slow start, congestion avoidance, and fast retransmit. Reno from Jacobson some years later that introduced the mechanism or algorithm of fast recovery. The new Reno, Jacobson 2, that propose a fast recovery improvement. Vegas, proposed by Brackmo and Peterson, and that proposed a congestion avoidance based on round trip time. That is, in order to detect earlier the congestion, detecting that there are an increase in the round trip time due to the soft congestion in the network. And finally, other proposals as SAC, DSAC, BIC, and cubic. We will explain slow start, congestion avoidance, fast retransmit, and fast recovery. Then the congestion control, the slow start algorithm. The problem is the initial congestion. If the TCP entity, once the connection is established, sends the data with the throughput given by the advertised window and the round trip time, it is most likely that it will generate congestion in the queue of the first link with less capacity than this throughput. That is the throughput limited by the advertised window divided by the round trip time. Solution, congestion control with slow start. That is, at the beginning of the TCP connection, the transmitter set the congestion window to 1 maximum segment size. Each time it receives one acknowledge, it increases the congestion window by 1 maximum segment size. If we see this in this diagram, we could realize, in fact, that each time, for instance, at the beginning, the transmitter sent only one segment with of MSS, of a size of MSS. Once the transmitter received the first ACK, the window is incremented by 1. That is, now the congestion window is 2. Then the transmitter could send 2 segments of the maximum size of MSS size. When the transmitter received the acknowledgement of the 2 MSS segments, the congestion window is increased by 1 with each acknowledgement. then now the congestion window is equal to 4 MSS. Then the transmitter sends 4 segments of maximum size. And after that, once the transmitter receives the 4 acknowledgements, the congestion window is increased to 8 MSS. That is, then here we could see that the congestion window increases exponentially. And this is typically the graph, the chart that represent the evolution of the congestion window based in the evolution of the time measured in round trip times. The first round trip time, we double from 1 to 2, after from 2 to 4, after from 4 to 8, from 8 to 16, from 16 to 32, and from 32 to 64. And this is typically an exponential increase or increment. And then this is typically the slow start phase. Well, then now we have another problem: how to achieve the highest throughput while avoiding congestion. If the TCP transmitter entity continues to increase the throughput, increasing the congestion window with each acknowledge, at some point a segment loss may occur due to severe congestion. The solution: implement the congestion control with congestion avoidance. When the transmitter detects the segment loss because the lack of the corresponding acknowledgement, it assumes that it was due to severe congestion. Then drastically reduces the throughput, setting the congestion window to 1 MSS, restart the slow start process, and sets the variable slow start threshold to half the value that the congestion window had when the loss of the segment was detected. When the congestion window, during the slow start phase, when the congestion window reached the slow start threshold, the transmit will go into the congestion avoidance phase. And in this phase, every time the transmitter receives an acknowledge, it increases the congestion window by this fraction. But if we see this detail, we will see that with this fraction, if we, for instance, in this case, we have a congestion window of 4, for instance, MSS, and we receive 4 acknowledges, then each acknowledge, we increase the congestion window by 1/4 of MSS. Then, for instance, with 4 acknowledgement, we increase the congestion window by 1 MSS. And each time a round trip time happens, then the congestion window will increase by only 1 MSS and not doubling the congestion window. That's why then at each round trip time, the number of acknowledged increased by 1, then the congestion window increase linearly, not exponentially. And this is typically the graph, the chart that shows the evolution. The evolution typically here we have a segment loss. Then we reduce the congestion window to 1, and we set up the slow start threshold to 32 because it's the half of 64. After that, the slow start will restart, then starting from 1, 2, 4, 8, 16, 32. When the congestion window reaches the slow start threshold, the behavior of the algorithm changed to the congestion avoidance phase. In the congestion avoidance, the congestion window is incremented only by one every round trip time. And that's why the evolution of the congestion window is linear and not exponential. Until, for instance, there is a new segment loss. In that case, then we reduce the congestion window to 1. We set up the SS threshold to half of this congestion window. That is typically the half of this is this value, and restart the slow start process. Then the congestion window will be increased exponentially until the congestion window reach the value of the slow start threshold, and after that the phase of congestion avoidance will increase the congestion window only by 1 MSS each round trip time. And then this is typically the first proposal where we use typically slow start and the congestion avoidance in order to implement the congestion control. Then some new enhancements were proposed to implement the congestion control in the different TCP entities. There are two algorithms called fast retransmit and fast recovery. Then fast retransmit and fast recovery are used to react more quickly to the jam situation after a packet loss. For this purpose, a receiver informs the sender if packets arrived out of line, and thus there is a packet loss in between. For this purpose, the recipient reconfirms the last correct packet for each additional incoming packet out of line. This is called duplicate acknowledgements. We will see this. The sender notices the duplicated confirmations, and after the third duplicate, the sender immediately resends the lost packet before the timer expires. Because there is no need to wait for the timer to expire, remember the RTO, the retransmission timeout, the principle is called fast retransmit. The dupacks are also indications that although a packet loss took place, the following packages have arrived. Therefore, the transmission time is only halved after the error and not started again with a slow start as with the timeout. In addition, the sending window can be increased. The sending window, that is the congestion window, can be increased by the number of dupacks because each stands for another packet that has reached the receiver, albeit out of line. Since this means that the full transmission power is reached more quickly after the error, the principle is called fast recovery. And this is the chart, the graph that shows the different behavior implemented using fast retransmit and fast recovery. In this case, then, we have the slow start phase. We have the congestion avoidance phase here, and we detect a packet loss, but a single packet loss. That's why we receive dupacks, that is duplicate acknowledgements. Then when we detect earlier the packet loss without waiting for the retransmission timeout. We could retransmit faster, and at the same time, we only reduce the congestion window to the SS threshold, to the slow start threshold that is set up to half of this value, instead of reduce the congestion window to 1. And after that, we continue, we reset, in fact, the congestion avoidance algorithm instead of the slow start algorithm. And in that way, we react quickly to the packet loss, but typically not due to congestion, but due to or very low congestion or to an error, for instance, an impulsive error that change only some bits in only one segment in the network. Then we will see deeper than some details. Remember, we have this error control. In this error control, if the loss of a segment is due to errors, for example, due to impulsive noise, not due to congestion, not a burst loss, when a severe congestion happens, typically the several packets or segments are dropped. Then, if there is no severe congestion, but only some errors in the network, we perhaps only lost one segment and not several segments. Then each time the data arrives to the destination, in fact, the receiver the receiver will send an acknowledge indicating that the receiver expects to receive the segment that that were lost, that were dropped or lost in the network, and those data are received and stored in the receiver buffer, but only but those data segments are not acknowledged because the receiver lacks this information. In order to react to that kind of phenomena, we need to wait for the timer expiration, the retransmission timer expiration. That is, we need to wait for the retransmission timeout in order to retransmit the data that loss in the network. Then, problem: how to achieve faster retransmission without waiting for the retransmission timeout. This is the problem. This is the challenge. We need to implement some solution to this problem. Then the solution is error control with fast retransmit. And when the transmit receive 3 duplicate tags, this, and this, it assumes that the segment indicated in the acknowledge number was discarded or lost, and retransmit immediately the segment from starting at this sequence number without waiting for the retransmission timeout. And in this way, we accelerate the retransmission with this fast retransmit algorithm. In the case of congestion control, remember fast retransmit is related with error control. And fast recovery is related with congestion control. Then, which is the problem? The problem is how to prevent the channel from emptying after a fast retransmit. The idea is we need to use optimally the bandwidth of the channel. Then we need to prevent the channel from emptying after a fast retransmit. When the transmit detects the loss of one segment, it lowers the congestion window to 1. That is, it enters slow start even though there is no congestion, for instance. And it takes several round trip time to reoccupy the channel. Remember this chart. This chart. If we detect a segment loss and reduce the congestion window to 1, we need several round trip times in order to occupy the channel again, and perhaps we could transfer at this rate, but we only lost one segment, not several segments. Then there is no congestion. There is simply an error. Then we need to solve this in this way. That's why we use this solution, the congestion control with fast recovery. When the transmitter receives more than 3 duplicate tags, it detects the loss of one segment, does fast retransmit, but lowers the congestion window to the value of the slow start threshold. That is to halve the congestion window with at the time of detecting the three acts duplicated or dup acts. That is the fast recovery algorithm is we detect the three duplicate acts, then the SS threshold is set up to the half of the congestion window, and the congestion window is set up to this number, to this SS threshold, and we don't enter to the slow start phase. Then that's why in this chart, in this graph, we could see, well, the slow start, the congestion avoidance, and here we detect the three dupacs. Then we perform a fast retransmit. We set up the SS threshold to the half of this, that is to this value, and to set up the congestion window to this value, and restart the continue with the congestion avoidance algorithm, that is increasing linearly the congestion window. And that's why in this way the TCP implement those mechanisms of congestion control and other mechanisms. Remember, all the mechanisms that are implemented by the TCP are enumerated in this slide. I don't remember the number. This one. Remember, TCP implement the multiplexing of inter-process communication traffic with using the port numbers, is byte-oriented full duplex, is a byte-oriented full duplex transmission, implements segmentation, that is the byte stream is is sent across the network in segments. Remember, the segments could have a variable length, but with the maximum of established by the MSS, by the maximum segment size that is negotiated during the connection. The TCP protocol implements a sequence control. That is, if the segments arrive to the receiver out of order, the TCP with using the sequence number could reorder the data in the receiver buffer. The TCP implements a mechanism of automatic repeat on query with a sliding window, go back in. And this mechanism permits to implement an error control algorithm. With that error control, the data is each time the receiver receives a segment correctly, the receiver sends to the transmitter an acknowledgement. And if the transmitter doesn't receive the acknowledgement of a segment after a retransmission timeout, the transmitter retransmits the segment again. The TCP implement another mechanism called, always with this concept of ARQ sliding window, implement a mechanism of explicit flow control, where the receiver send an explicit information about the availability, the space availability in the receiver buffer, indicating the window size, that is what we call the advertised window, and then the transmitter will use that window size to implement the automatic repeat on query sliding window. But if there is congestion, there is congestion in the network, that situation is detected implicitly by the transmitter of the TCP entity, and the entity, the TCP entity, detects implicitly the congestion situation when the acknowledgement, when, for instance, the round trip, the transmission timeout expires, and segment need to be retransmitted. In that case, the TCP entity assume that the loss is because there is congestion in the network. Then the transmitter reduce drastically the congestion window. If the congestion window is lower than the advertised window sent by the receiver entity, the receiver entity of in that flow control, then the ARQ you will use the lower of the two windows, the window advertised by the receiver and the window calculated or estimated by the transmitter. Well, that's all related with the TCP protocol. Then simply we already explained different aspects of the TCP, and I suppose that those are the learning objectives of this chapter E, the last chapter of the TCPIP protocol family. You know the tasks of TCP and can explain the communication process, including setting up and disconnecting the connection. Remember the three-way handshake and the four-way handshake in order to close the connection. You know the structure of the TCP header and can explain the fields. Remember the different fields. You can explain the principle of TCP Window Management, the ARQ, the automatic repeat and query with sliding window. You know the methods of for overload control of TCP, that is the two methods, the flow control and the congestion control. You are familiar with the bandwidth delay product and can explain its importance for overload control using window control. Remember that the bandwidth delay is when we calculate which is the optimal window that we need to use if the channel present particular bandwidth, for instance, measured in bits per second, and the channel present some particular delay, some particular end-to-end delay, that is the typical round trip time delay. And then when we multiply the bandwidth with the round trip time delay, we could calculate which is the optimal window that we need to use in order to use all the channel, all the bandwidth of the channel. If the window is lower than that bandwidth delay product, in fact, we couldn't be able to use all the bandwidth of the network between those two end systems. You can explain the determination of the overload window with the slow start and congestion avoidance phase according to Van Jacobson, and you know the methods of fast retransmit and fast recovery and can explain them. Okay, that's all.